Today I'm going to be talking about Postgres and its use as an embedding database. And I want to talk specifically about Postgres in the sense that it can give you some innovative searches that other uh, vector storage solutions don't actually give you. My name's Steve. That's the Steve Zero because I'm lead like that. That's where you can find me in most places. And I work as a developer advocate at Voxel 51. So let's go ahead and get started. So the agenda for today is the demos. Like I want to show some demos so you can actually see what's going on rather than just talk. We'll do a few slides, then some show and tell. I didn't bring any milk and cookies, sorry. But then finally some imagination games. And I'm going to show you uh, current hybrid search, why PostgreSQL, some demos, and then some fun after party games. Right? The main point of this entire talk is PostgreSQL allows more than just sparse and dense vector search. Right? That's typically what we see when we talk about hybrid search, is that we're going to use sparse and dense vectors, which is interesting and really good. There's just more that you can do out there. Mark Twain had something to say about this, was always start with PostgreSQL, then if and when you need more, look to other solutions. Thanks, Mark. And then the next point, this is the secondary point, do as much as you can on the server. Especially with database solutions, if you're doing it, try not to bring your data back and forth over the wire. If your data is already in the database, try to do the manipulations or operations right there on the server. It's usually a better machine, and you don't have to eat all those costs of serializing, deserializing, moving data all over the place. So Sun Tzu had something to say about this, which was keep operations as close to the data as possible and minimize data over the network. This is how you defeat your enemies. And then Rabbi Akiva chimed in with, to be a good person, study SQL deeply, the rest is commentary, all right? So just keep these ideas in mind from our great thinkers of the past about how to deal with SQL databases and data in general. So PostgreSQL lets you move beyond hybrid, which is equal just to sparse and dense vectors. And when I say sparse vectors here, I'm thinking of something like Elasticsearch, the Lucene-based model, and dense vectors, stuff coming out of transformers, right? And typically what we do is we try to combine those two together to give us a better text search. So let's just go straight to some demos, all right? Before I switch slides, we're gonna do a dense vector search. Then I'm gonna show you simple hybrid, and then I'm gonna show you some spatial hybrid, okay? So let's click over to Edge, kick out of the show, move our demo bar so I can actually see the tabs. There we go. Let's go ahead and start with this one. So this is running in a GitHub code space. The link, you can run it as well at home. You just go ahead and click that link for that in there. I'll give the address for the slides at the end of the talk, and you can run this whenever you want. And there's instructions on how to run it too. What we've done in this demo is the Alexandria project has gone ahead and embedded, using the instructor XL model, they went ahead and embedded all of the archived abstracts at a certain point in time, right? They snapshotted the archive abstracts, AR, well, I said ARVIX, that's a typo, and I leave it there because it changes some things, but it's archive, right? And they actually snapshotted it, used the instructor embedding, and then put those embeddings together with some metadata, particularly usually just the full text of the article together, right? And so what I have done is uploaded those embeddings into Postgres into a vector column store, and then we're going to just do some queries on it, right? So just to show you how you specify the data to be in a embedding vector, right? So this is the create. I'm sure most of you know SQL. All you need to do with work with Postgres is know some SQL and learn some operators, and that's it. This is how you actually make a column. You add the extension, right? You add an extension vector, and then I'm creating a table that has an ID and some text for the abstract, and then you say an embedding vector and the length of that vector. And then that's it. And now you have an embedding vector in there, right? It looks very much like standard SQL. It's just a different data type for a column. And then we just put stuff in there, right? Which is not that big a deal. So I'm going to go ahead and show you the queries. So this is the straight queries. The first query we're going to do is we're going to search for something similar in the sentence to the archive query, right? So the instruction given to the instructor model was represent the research paper abstracts for retrieval, and then the input. And then here's the sentence that we're going to use to query it. And so right now we have, how about we do something related to Brent's stuff, which is robot object detection. Right? So we're going to look for abstracts related to robot object detection. Sorry about that. And so then this is just the similar search. And so when I teach this, usually what I tell people is the hard part is learning everything up until the actual vector search, because typically I'm not talking to an audience that knows neural networks and then transformers and embeddings. And so I have to teach them all that background. So I'm assuming most people here already understand embeddings, so I don't have to describe how they come. So this is much more fun because I can just get right to the meat of it. This is the only thing you really need to learn to do vector search. It's a new operator inside of SQL. What that says is calculate the distance. Right? That's all it's saying. So if we look at the query to just do a normal similarity search, we're going to select the ID, then we're going to select the distance as distance. I want to see what the distance is. And then the abstract from the documents, order by, again, this is the same as that. I'm just saying order by the distance, limit 10. And the rest of the statement is just normal Python. Right? So I'm going to do two queries at the same time. I'll show you both of them right now. The second query we're going to do is because we're using the cosine vector space. I forgot to tell you that we're using cosine distance in the embedding vector for the index. We can do this simple dissimilar search. So it's as easy as in SQL is just the exact same statement, except this time we multiply our embedding by -1. And that's it. And that'll give us the ones that are most dissimilar to what we have. So let's go ahead and run this. And then you all know we're going to have to wait a little bit while it loads up its stuff. I'll show an example in the next one about how to create the HNSW index inside a PG vector. Are there any questions right now? No, there's no questions yet. If you have them, now's a good time while we wait for the model to do its thing. Uh-oh, come on. No questions yet. All right, almost ready. And go. All right, so now it's downloaded all the stuff it needs. Now it's loading the instructor model, and we're going to wait for it to do its query. Once it gets all this stuff loaded, it's actually quite quick. This is just all the loading stuff, which I'm sure all of you are familiar with as well. Oh, there is a question. Yeah, why we're multiplying by -1. The question is why multiply by -1 to search for the farthest? It's because if you think about something, if you think in a 2D plane, right? If this is your 2D plane, this is the X and the Y axis. If something's up here and you multiply it by -1, it does the mirror reflection of it into the opposite space, right? So if we say, hey, find me the things that are closest to this thing that's opposite of what ours is, then that should be things which are really dissimilar to what we're doing. Does that make sense? I hope so. All right, so let's go ahead and look at our results. This out of the way. All right, so similar search for robot detection. We were saying looking at robots and object detection. And so the articles you can see right away, avoid a robot is mean robot who is designed. There's also these things which are object detection and robotic, right? So doing a pretty good job. This is all truncated because if I put the whole abstract in, it's actually quite hard to look at, right? And you'll notice that those distances are relatively small. Then if we do the dissimilar search, we can see that those abstracts are quite dissimilar from what we were expecting with the robotic search. It's just basically saying the thing that's most far. This is the first time I've seen this. That's why I'm laughing. I think that's hilarious. The things that are most distance are ones that are saying this paper has not yet been accepted for publication or withdrawn by the authors. So that actually has absolutely nothing to do with robot object detection. And you can see these distances are quite big compared to that one. So that example was just to show you a very simple embedding search and how easy it is to do. I think for most of you, this is not a fancy thing or a hard thing, right? You just adding a new operator in, which is actually quite easy to understand what it does. It just says find the distance, right? So, and then now you can do all the other stuff you know in SQL on top of that distance operator. The next example I want to do with this one is we're going to do a hybrid query. So some people don't know this, but Postgres has a full text search engine. The whole tokenizing great full text engine search. So we're going to do both queries, and then we're going to combine them. And then what I'm going to do is do like the very most simplest re-ranking, right? I'm just going to use reciprocal rank fusion, right? So, and that's it. And then we'll come up with our answers, right? And so in this, what we do is, this is the actual full text search, right? I built a full text index. There's links to the documentation on it in my talk. But what we're basically saying is turn this abstract into a vector, do a query on it, and then look for things that are close to it or match it, right? And descend by 40. And then what we're going to do is our sentence or full text we need to use, because the full text search is actually doing token based, we need to give it the tokens we want, right? And this can be really helpful if there's something, hopefully um, this should be closer to the answer we want, because we say, look, we really want the words robotic and detection in here. And if those words are in there, then rank this thing higher, and they should come back more in our results, right? And then this full text search, this is creating the full text index, and then we're done, right? And then for the other one, it's the same thing we saw before, right? So that's the full text search. It's going to show us the results from the full text search. The other one before is we're going to change this to the same words that we set up as it again, but I've already forgotten what those words were. So robotic detection. All right, so we're using that same phrase again to look for articles that are similar now. Now we're doing a similarity search using transformers. Same model again, of course. Same exact query again. Just give me the distance and then sort by distance. And then once we've got that, we've got the sparse scores and the dense scores, sparse being full text, dense being embeddings. And then we just do a reciprocal re-rank, right, and just put them together and re-rank them. So most of you have probably seen that, but I'm going to show you how to do it here. But you can do it actually in the same database. Like, it's not like you actually have to do Lucene and then do something with embeddings and then have it do the results that way. It is going to go, isn't it? Any questions on this while we're waiting to see what it's thinking it's doing? There we go. It's all done. I don't see any questions. All right. So here you can see this is the this is the re-rankings. No, this is actually the full text search. Sorry about that. It's still doing the other search below. So this is actually what it gave back for um, the full text search, right? For those two keywords. Who knows where those words actually are in the abstract? They could be much farther in the abstract. Again, I'm truncating because it just ruins the output. And so what you see here is there is 36 results that overlapped of the 40, so that's actually pretty good. And then what you see here is the re-ranking of the article. So this is the ID and the score. So if we looked at the full text search, that was not the highest full text search, right? It's 62647. Let's see if we can find that. This one, lens modeling is the key to successful in meaning, and something else in there, right? But so you can see that this one, because of the dense and sparse being re-ranked together, another article ostensibly has much more in the dense vector search, and so that re-ranks it as number one, right? It's probably high in the sparse vector search as well. Yeah, so it's there, and then it's there. So it got ranked down to number two. Sorry, I was reading them backwards. Number three, actually. So That is doing hybrid search in PostgreSQL. Uh, so the normal NLP stuff that you would do, you can just do that easily in PostgreSQL, and you don't have to switch to another database, and you don't have to move your data anywhere else. The other one I'm going to show you now is image search, because we all love images. In this one, I've modified the Google Geo Landmark survey. I actually went through and grabbed about 1,000 of their images, or 100,000 of their images, sorry, and found X and Y coordinates from them. Some of the Wikimedia pages had X and Y coordinates. I attached those coordinates to the image as part of the metadata. And Postgres has probably the gold standard in spatial analysis um, in a database, which is called PostGIS. And so what I do is I store those coordinates as PostGIS features, and I can do my search using both the dense vectors and a spatial search. And I'm using the most simplest things that PostGIS can do here just to give you an idea. So first we have to actually make uh, sorry, oh no, this one already has it all. Sorry. So what we're going to do first is we're going to do our queries, right? Oh, the image that we're actually going to search against is this image right here. Okay, so trees with some vertical structure, nice lot of green. This test images is if you run this yourself, you can move these images into the query image. The code just says whatever's in the query image, find me images like that. So in this case, I've already loaded them all again. We're going to do the query. So this one, we're going to basically do a query that's going to be just the images first, right? And so what that has is I'll show you where the DB query comes here, right? And so what we're doing here for just a normal vector query is the same as before, right? Just that operator. Okay. And so then this one includes the spatial. And so you can see we still have that distance calculation. We have the name of the file, the URL so that we can look at it. And then here comes the spatial part. So we're going to collect it from images. And then I added a table that has the out borders of all the countries in the world. And they're indexed by their 2-letter ISO name. And so I'm going to say, find all the images where the ISO equals the 2-letter country name, and that 2-letter country, the boundary for that 2-letter country name covers our location, right? And then I just order by the embeddings, right? So this is the spatial part right here, these two. This is normal SQL, right? Where ISO equals whatever, that's just finding a 2-letter word and then saying based on those two letters, find all the geographies that cover the images that we want. All right. I hope that makes sense to people. So let's go ahead and run this. And we're doing Canada here, but I could switch it to somebody else's favorite country if they wanted to. Again, we're going to load the model. Any questions on this? Um, Sudeep, no, I don't actually. With databases, you never want to put the images, well, I shouldn't say never. It's highly unlikely you're going to want to push those images into the database. What you usually do is in the metadata, you have a link to where that image is and then pull it that way. Okay, so something went wrong, but let's see what happens. Here's with the non-location based, right? And so if I pull that up, if we copy that URL, and we paste it, you can see it's also a forest, right? So it found us really nice ones it's green, it's got some vertical structure. We can go down the list and see more that are like that, but that was an image-based search. I don't know why it's saying, oh, I know why, I think. I think this is the problem. This is weird. I don't know why. Let me try this, doing this to do just the DO search. It should have returned right there, but I don't see where it did. So let's try running it one more time. It should be faster since it doesn't have to load the models again. No, I don't. Line 11. Oh, it's having a problem here. That's why it's bombing out. All right, so let's just comment these out. Oop. Sorry, I didn't catch that before. Actually, we'll just delete them for now. And then I don't know if we need this, but let's see. Sorry, I don't think that quite that fast on my feet.
We do have a comment in the chat that said the results are undefined.
Yeah, I don't know where I've defined them. So I'm not gonna. You don't want to watch me debug. That's no fun. It worked now, right? There was something about me needing to remember to move these out to get rid of that. So this was our original query. Remember that one was in Germany. It's this one here. Now I have said, let's constrain it to Canada. And so what we're going to get for that image should just be in Canada. So if we go to this one, that's what we get in Canada, right? And so you can see it's in Quebec. So what we've done is been able to do a hybrid search using not sparse and dense vectors, but to be able to say, I want it in this country as one of the hybrid features, and then similar, right? And so those are two examples. The code is there. I should probably document that a bit better, but we've got both of those working. So I showed all three of these. These are links to them. So if we move on to the next slide, there's other hybrids you can do. So I showed spatial data. These are all the other data types that Postgres supports. It supports a JSON data type, just like Mongo. HStore is a key value like Redis, right? So you can do searches that are searched by, look for something in the JSON and for a similarity search, or something that's in the key values and the similarity search, or all of those. It could be JSON, spatial, and similarity, right? You can combine any of these and it's all just going to be in the same SQL. You can do a graph search. You can do an XML search. There's two different time series databases. This is a cube, so if you have cube data sets, you can use that. And this is the one that I want to show everybody. It's called FDW. It's foreign data wrapper. Postgres has this ability to take a foreign table or file and make it appear as a SQL table inside the database. And the reason I'm showing you this is because I want to show you the list of things that can be wrapped and then appear as a table, right? So these are all different foreign data wrappers. So CSV files can appear as a table, JSON files, Parquet files, tar files, zip files. These are different geodata types, LDAP, generic web, right? RSS, you could make it look like a table. And then there's like Dynamo and all these other ones. There's big data ones like Elasticsearch or BigQuery. There's column-oriented ones. There's scientific wrappers. I don't work with genomic data, but I'm sure that's great. Here you can, I don't understand what these are doing with the object system wrappers to make them look like a table, but password I do, but I don't know what it's doing with Docker. And then the exotic wrappers, right? And then there's some examples if you want to write your own. So I think that's actually a really incredibly powerful feature in that you can bring in arbitrary data types, make them appear as a sample, and then use the similarity search along with these arbitrary data types together in just a simple SQL statement, and which you can store as a view, right? And so in a view, you stored that query and someone just has to click on the view of that table or look at the table and it's already done the query for them behind the scenes. If we go back to the slides, I'll show you the next thing that's interesting, hopefully, which is these are other helpful AI/ML extensions available in Postgres. So PG Vector is what we use today for vector, but there's another one called PG Vector Scale. I haven't compared and contrast, I just use PG Vector. There's PL Python and PLR, and this is the one that I think is actually one of the ones that's my favorite. You can actually use Python or R as an embedding language for functions inside of Postgres. So you could actually, a trigger is that when something comes in, when something's written to the database, an action is performed, some sort of function or SQL function is performed every time it's done. You could actually take the Python code that does the embedding, and every time a record is put in, you could have it automatically populate a column that was embeddings, without having to go through any other code, right? So you don't have any of um, the data scientist can write the Python code, put it as an embedded function, and then the DBA doesn't have to duplicate that, and no application developer has to duplicate it. They can just call that as a function from then on to calculate embeddings. There's a PostgreSML. This is a machine learning library. Madlib is the same. PGAI, I haven't played with it yet. PGGPT plugs you into a GPT model and lets you go back and forth and have a discussion to figure out what you want to do. DuckDB, yet again, another great way to incorporate other databases or data formats into your Postgres is to use DuckDB. And so this is an extension that allows you to have DuckDB as another data source. Greenplum and Citus, these are two other extensions. These are for if you have really large data sets and you want to start getting into a lot of parallel processing. Both of these know how to handle that. TableFunc is some things that helps you make crosstabs and things like that with your data. If you wanted to actually work without doing a foreign data wrapper, but just wanted to use Parquet files directly, you can do that. If you're familiar with Apache Arrow, there's one for that. PG Strom, you can actually use the GPU in the database, like use it for analysis. And I forget what Parade DB is, but it's something machine learning. So these are all ones for you to check out after. So the big take homes on, I think this is fun, right? Because I get to play with lots of different data types. I'm not just constrained to just the embedding. I can take the embedding plus other really interesting stuff in what you would typically call the metadata, but you can do a lot of other great things with it. It's powerful. I mean, it's really powerful. To write that spatial search with just the embeddings and some normal metadata, I've seen a lot of different people re-implement the wheel trying to do that spatial search, right? And I've seen a lot of other vector databases re-implement the wheel trying to do that vector search when it's already right out of the box. We just scratched the surface. I just showed you two simple examples. Don't take my code as production code. That was just to demonstrate how things work. You can mix and match any of the things we showed today, just like I said. And my big advice is when in doubt, start with Postgres. So if you're looking for an embedding database, always start with Postgres. If you're looking for any data store, start with Postgres because it's probably the case that Postgres has some way to handle the data that you're working with. And you already know it, and you probably already have Postgres in your infrastructure. So it's just an easy way to get started with these things you're trying to learn, and it scales quite well. I mean, it's the same as the Mongo story from way back when Mongo came out with JSON, which is if you're going to do a gazillion JSON objects, or you're going to do a gazillion embeddings, you know that Postgres is probably not going to be the right one. You might want to look at more specialized one for that one. But everything up to that, which is a lot of people, I think you should start with Postgres, and then if it doesn't work, go back and read the documentation one more time, try it again, and then if it doesn't work, think about a specialized solution. So my last advice to you is Postgres, all the things. Um, this is the link for the slide deck right here. And again, that's me.